Okay, the first problem on today's document, you have 4 wires, different diameters, different lengths. And we're going to assume the same voltage on all, unlike the problem as it exists on the document. These two have the same voltage on that document, and these two have twice the voltage as this one. Okay, so what we wanted to do, here we have diameters, here we have lengths. And what we want to do is we want to order the electric fields of these in these wires from least to greatest. Okay, now if the voltage is the same on all, and you might consider how this changes if you use the voltages on the document, but if the voltage is the same in all, then the electric field is simply going to be inversely proportional to the length. Greater length, lesser electric field, because the electric field is basically the spread of your voltage. It's the voltage divided by the distance over which it's spread. Now we assume these are uniform wires. Wouldn't necessarily be true if the wires weren't uniform. So the shortest wire is going to have the greatest electric field. And going from least to greatest, and I don't know that these numbers make any sense. Did I confuse these two columns? I'm going to have to stop here and correct that if necessary. Okay, well, clearly the longest will have the least electric field. So listening least to greatest, here's the least electric field. Here's the next longest, which is going to be the next least. And I think I just wrote these numbers down carelessly. This is the next longest, so it'll be the next least. And this is the shortest, so it'll be the least electric field. The greatest electric field, okay? And I think maybe I was confusing least to greatest when I wrote some of these things down. Now, we have the hypothesis that somebody mentioned that the volume might be the thing that determines the electric field. And in which case, here we have clearly the least volume. We have the shortest wire and the wire of least diameter. That's clearly going to be the least volume. And then how do we compare the others? This is the next shortest, and it has the next to the least diameter, so it's going to be number 2, going from least to greatest. And then how do we compare these two? Well, they have lengths that aren't much different, diameters that aren't much different, but remember that the volume goes as the square of the diameter and the length. When we square the diameters, we get 25 and 16. Now, it's probably clear enough what the comparison would be if we just thought about the diameter. If we go to the squared diameter, this is 25. The ratio between the two areas is going to be 25 to 16. That's like 1.6 something. And the ratio of the lengths is like 0.9. This is 0.9 as long as this, but it has 1.6 times the cross-sectional area. And we need to think about these things. Now, proportionality in this type of reasoning is not something that's taught very much or very well. But it's very, very important, so you do need to try to focus on it. And I do want you to reason out this whole problem using this type of reasoning. In any case, the volumes then, this will have less volume than this. So the order from least to greatest, this will be third, this will be fourth. Now, the volume turns out not to be related to much of anything, so I'm just going to kind of put a circle around that and lightly cross it out. It's a good exercise in making comparisons by proportionality, but it's not going to be relevant to the questions about the comparisons of electric fields, currents, and so forth. Okay, so now we want to order the currents. Okay, well, remember the current is proportional to the electric field and the cross-sectional area. So here we have the least, here we have the greatest electrical field. If we compare the cross-sectional areas with, well, take the cross-sectional area of each wire as a multiple of the cross-sectional area of the thinnest wire. So we're calculating cross-sectional area of the wire over cross-sectional area of the thinnest wire. The thinnest wire, of course, the ratio is going to be 1. And that should be completely obvious. For the second, well, the ratio of the cross-sectional areas is going to be the ratio of the squares of the diameters. So you have a diameter 5 here compared to a diameter of 2 here. Your ratio is going to be 5 squared over 2 squared. 25 fourths comes out to 6.25. So this one has 6 times, over 6 times the area of this one. Now it has a lesser electric field, but it's going to have 1/3 the electric field, 6 times the area, so it's going to carry twice as much current. Okay, that's fairly straightforward reasoning, but you got to practice it a little bit. Okay, well, here we have 2.25 as the ratio of the areas. Ratio of the lengths is like 1.6, so we have over twice the area, less than twice the length. That's going to lead to a greater current than we have here. Okay, on this one we have 4, diameter 4 compared with diameter 2, we're going to get 4 squared over 2 squared. That comes out 4. I didn't bother writing the calculation. We've got 4 times the area and a little more than 3 times the length. Remember, the area tends to multiply the current. The length is going to be divided. So with not quite 4 times the length, but 4 times the area, this one will also have greater current than this one. So this clearly has the least current. Now, making comparisons between the other pairs, well, we can reason them out similarly, and you should do that. Now, just to quickly summarize this before we go on here, the current is going to be proportional to the electric field and to the cross-sectional area. Greater electric field means greater current. Greater cross-sectional area means greater current. So to get the comparison between 2 wires, we multiply the ratio of the electric fields by the ratio of the cross-sectional areas. The ratio of the electric field between this and this is 1/3. This has 1/3 the electric field of this, but this has 6 times the cross-sectional area. So when we multiply that out, we've got something like 6 times 1/2. This will carry about twice the current as this one. Similar comparison for all the rest. And we don't want to just do this without reminding ourselves of how we got the ratio of the electric field or how we got the ratio of the cross-sectional area. It's not just a calculation, it's an understanding that goes back to our direct experience of currents and voltages.